Okay, it looks like it is. It's beeping. All right. All right, so sorry those at home. I started with the notes. Actually, sorry people in third period. Got to kind of listen to this all over again. So print those provided notes, and then we're just talking about probability, likelihood of something happen. Sample space. Standard die has 6 sides. So what are my possible outcomes? Either roll a 1, 2, 3, 4, 5, or 6. That's listing a sample space. Next thing we were talking about is making a tree diagram, which is provided in this because it is a lengthy process. Not that we are going to draw some tree diagrams in later ones. But how many different pizzas can you order if you can get a large or a small, square or round, thick or a thin crust, and only one topping, either pepperoni or mushrooms? Well, these tree branches represent all of the possible different pizzas that could be ordered. There's one. There's another. I don't want to hit every single one of those, but all of these total branches represent unique, different pizzas based off of maybe just one little difference, maybe more. So, what does each outcome on this branch represent? Unique pizzas. There is at least one difference, if not more. So there are 16 unique pizzas you could order under these parameters. All right, now this is the part of your first part of the homework. By the way, I made a mistake. I was thinking globally of like the first couple days, and I accidentally put 9 through 12 on your worksheet. Go to your worksheet real quick. 9 through 12, just kind of say do not do right now. I don't get to those. I'm going to start with that tomorrow. But when I was making this worksheet, I accidentally thought of those questions and put those in there. So 9 through 12, you do not have to do for tonight. So it should be a really short assignment, just getting the idea down. Okay, so how many possible round pieces? Okay, you got to really pay attention to that. How many possible round pizza specials can you order? And then list the sample space. So here's what we got to do. We're going to keep the sample space in order the way they have it up there. You can either order large or small, square or round, but in this case, they only want to know how many possible round ones there are. So really what we're going to do is list these sample spaces. Only the round ones. So this one, and then this one. Oh, I'm sorry. And then this one, and then that one. But then also we could have all of these, all right? So we could see that there's only 8 out of the 16 that this happens, and we should have been able to figure that out before anyway, all right? That there's only 8 possible round ones. So how am I going to list that as a sample space? Well, I'm going to use my braces. We'll have large, and then I'm going to put R there for round. Last hour I put a key off to the side. I think we can figure it out. All right, then I think for thin or thick, I could put thick like TK. That's what I did with the other class. There's the major different letter between thick and thin. And then pepperoni or mushrooms, easy. Pepperoni, P. Or I could do a large, round. Let's stick with thick and then change that pepperoni to mushroom. And then let's finish off the larges. It could be large, round, thin, TN, and then pepperoni. And then large, round, thick, TK. Thin. This is still thin. My bad, dogs. That's thin, but then change the pepperoni. I thought I hit the eraser. All right, and then it's thin again, but then change that pepperoni to mushroom. All right, but then also I could have ordered small and then round and then all the other possibilities. So small, round. Let's take care of thick first. Pepperoni. Small, round, thick, mushroom. And then I'm off my page, but that's all right. Small, round, let's take care of thin. So just make a decision how you organize it in your head to get the 8 possibilities. Thin, mushroom. There's the sample space. That's taking from the tree branches listing out the possibilities in a sample space with the braces. I'll be lenient on the, if you use braces or not. They're sometimes hard to draw, and mine aren't the best anyway. How many of the possible pizza choices are square but do not have mushrooms? Okay, so square. So they are square, so that is, again, not round. So that's the opposite, but do not have mushrooms. We're going to only end up with 4 of them. Okay, so square. So we could have large. Let's do SQ for square. All right, and do not have mushrooms. So I could have a thick with pepperoni. And then a thin with pepperoni. So I'm taking care of all the larges. And then small, same thing. Small, square. I should have done thick first. Thick, not that it matters, but pepperoni. My K is getting a little crazy there. Small, has to be square. Thin pepperoni. None of these have mushrooms. That's the worst brace ever. Oh, let me make this finish right there. Maybe a little bit better. Okay, moving right along. Let's see if we have a tree diagram. All right, so you didn't create a tree diagram yet. One was given to you. So creating a tree diagram to represent flipping a coin and then rolling a dice. Okay, so when you go to your homework, there are some trickier questions, like number 7. You flip a coin 7 times and then roll a 6-sided dice. So that means you have 7 events before you roll the dice. Think about it as far as how you fill out your blanks mathematically, which I haven't covered yet. So that's not a tree diagram, but if you think of a tree diagram, that would get nuts. So number 7 is a bigger answer than you may think as far as the numbers are concerned. But let's just keep this simple. Flipping a coin and then rolling a die. This is a tree diagram. I'm going to go way wide here so that I get everything fitting perfectly. So we all know that you only have heads or tails as your first possibilities of flipping the coin. So there's your 2 choices. Then rolling a die. And the singular of dice is die. So do make sure you understand that. And understand every time we talk about dice, they are the standard 6-sided dice. So I could roll heads and then 1, 2, 3, 4, 5, 6, or tails and then 1, 2, 3, 4, 5, 6. And then I'm going to go back to this one and show you how we're mathematically going to do 5 through 8 without drawing a tree diagram. Okay, what is the sample space for the above probability? All right, this is where this gets a little bit crazy. You can get heads 1, heads 2. Notice I'm not drawing braces on here because there's a lot of possibilities and I don't really need them. I'll separate it with commas. And then the dash means, heads then, 1, heads then 2, blah, 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 blah. And then also tails, and then 1, 2, 3, 4, 5, 6. So keep quiet on that as I write this down. So understand a tree diagram, and then what it means to list the sample space when they ask you that. Again, 1 through 4 asks for the sample space. This is how you're answering 1 through 4. Okay, and then I'm going to go back up to these after we talk about the fundamental counting principle, how you're just going to mathematically do this. I think I'm going to use that space below for this here. So you can read that chart if it's too small up here in your printed copy. But you have frozen yogurt, vanilla, chocolate, strawberry, or peach, and then the fruit you can choose, and then the toppings. You can read. So I think you get it. Okay, and I'm going to go real wide on this. That's why I'm going to start down here because I know what's going to happen. You could either get vanilla. You could get chocolate, let's say CH. You could get strawberry, that's T seems fine. And then you could get peach. Ugh, I don't like peach. Okay, I like peaches. I hate fake flavored peach. It's just something that makes my stomach turn. And then after that, you can get bananas and cherries. Or cherries, sorry. Or bananas, cherries. Bananas, cherries. And of course, yeah. And then nuts sprinkles. Anyone see that commercial? I love that commercial. Anyone? It's one of my, it cracks me up every time I see it. Sprinkles. Geico? No. Nuts. Sprinkles. There is no other S word, so I'm just going to stick with S there. And then granola. All right, this one kind of got in the way. Do the best you can. This is why I tried to widen out. Last hour was real ugly. I was too close together, and then my last branches were kind of tough to draw. So it's a tedious process. Ugh. 3, 6, 9, 12, 15, 18, 21, 24. So how many different sundaes can be created with one flavor, one fruit, and one topping? All right? That's 24. That's what I just said. One of each. No mixing and no other that. Otherwise, it creates a whole different ball game, which is kind of tough to figure out, or tougher anyway in the beginning stages of this. Now, here's the fundamental counting principle of what's happening here. Oh, and I didn't actually have this written down. N times P. Okay, so sorry about that last hour, but I went backwards and showed that. So fundamental counting principle says that if event A can occur in M ways, B can occur in N ways, and C can occur in P ways, then the number of ways of A, B, and C occurring together is M times N times P. So I'm going to go back up to this. We're going to go backwards and look at all of our charts and show how we can actually figure this out faster. So what is the tree branch going to end up being? How many branches? We have flavors, and there are 4 different flavors. We have fruits that we can choose. There is 2 different fruits that I can choose. And then toppings, let's put top just right there. There's 3. 4 times 2 times 3 equals 24. So this is the fundamental counting principle. This is what happens when you do a tree diagram, how many branches you end up with. Going backwards to all the ones that we've done so far, there are 2 coins possibilities, and there are 6 possibilities for a dice throw. So flipping a coin and then flipping a dice, or rolling a dice. We have 12 different possible ways. Going back up to this one, notice I had 2 different sizes, 2 different crusts, 2 different shapes, then 2 different crusts, then 2 different toppings, only getting 1 of those toppings, right? And that's 16 possible different pizzas there, which is what we had in the tree diagram. So that is the fundamental counting principle. That is how you're mathematically going to easily do these questions. Now be careful though, this is where it does get tricky. I want you to look at number 7 again and think about it. I flip a coin 7 times, then I roll a dice. So you got to think about that you have 7 different blanks, 7 different things that happen before you roll the dice, and what are the possibilities. Almost giving you the answer there. But you have 5 shirts and 6 pairs of shorts. How many different ways can you leave the house dressed? Well, shirts, 5, shorts, 6. You have 30 different outfits. This is how easy it's going to be in some of these cases. Let's move on. Right? Anyone have any questions? All right? You could draw this out and say colors of your shirts and different types of pants. Tree it all the way out. You'd have 30 branches. right? And that's not what we want you to be doing. That gets a little bit too much. So be careful in reading this. You're making a pizza. You have a choice of 3 crusts, 4 cheeses, 5 meat toppings, 8 vegetable toppings. And then make sure you understand this, otherwise it would be a little crazy, especially on the toppings. If you could choose any of those 8 toppings, you'd have to do something else at the end here. But you're only going to choose one of those toppings. So 3 types of crust, then 4 cheeses, only choose one, only choose 1 meat topping, and then only 1 vegetable topping. This would be what would happen. It changes if you can add multiple toppings. It'd be rough. All right, and then you can calculate that and type it on your calculator. I'm not here to teach how to type 3 times 4 times 5 times 8. Does anyone have a number though? Did anyone do it? 480. 480. 480 different possible pizzas when you only have one choice. Imagine if you could do multiple choices on the last 2 events. Gets a little nuts. All right. She watched television from 12 to 12:30, and then another one from 12:30 to 1. At noon, her choices were 3. News? What kid's watching news? And then at 12:30, Friends? Is that still a thing? Anyone watch Friends anymore? My daughter used to. All right, then that kind of faded out. Oh, right now, Stranger Things is like the top Netflix watch. You know, it's moved. Anyone know why? Because they announced the 4 seasons coming up very, very shortly, so everyone's brushing up. I think I wanted to. I really enjoyed that show. So, Young and the Restless, Family Feud, or Chopped. Hey, I watch Chopped. Family Feud sometimes, but 3 choices at 12 to 12:30, 4 choices 12:30 to 1. So there was 12 different ways she could have watched these situations. All right. Yeah, I had this in my mind, and then that's why I kind of made a mistake in the word problem, or 9 through 12. So again, reiterate, 9 through 12 on your worksheet, made a mistake. I'll probably start with that tomorrow and then say, hey, all right, do 9 through 12 now, and then you could, get those finished before turning them in. But standard order for license plates is 2 letters, followed by 3 digits, and then another letter. How many different possibilities are there if, now imagine this, one state, there's a lot of cars. There's not just, like, we have 2 cars and we're looking to get a 3rd now that my daughter has her license. How many people just got their license this year? So it's kind of inconvenient not to have that 3rd car. So a household, it may have 2 to 3 cars. But then think of all the businesses and trucks. There's a billion trucks on I-80 when I come to work. You know, there are cars in Illinois all over the place. Trucks, business cars, home cars, 2 to 3 cars per family, per household in some events. There's a ton of different cars. So you need a ton of different license plates to have a different license plate for every car. So there's got to be a rule that makes those license plates happen so you have enough to cover each car in a state. So digits and then letters. Illinois, you could have all numbers, and I think you can have all letters. You know, it's one or the other. And then a combination of 2 is usually what you see throughout the whole license plate. So I don't know what the rules are for Illinois, but we're going to stick with this one. And then notice, this is usually the common thing. Letters and digits can be repeated within a license plate, and that usually is the case. So first of all, this always makes me sad as senior. How many, you're not seniors, but the last time I taught this was seniors. How many letters are there in the alphabet? This always drives me nuts. 26. People get that wrong, right? And you're leaving your Lockport education not knowing how many letters there are in the alphabet. If they can be repeated, then how many, two letters, good, I want to make sure I read it. How many possible letters can I put in the next position? 26. And then digits, this is the other thing that makes me sad. How many digits are there? Well, this one's a little different. How many possible digits are there? 10. What do some people put? 9, because they think 1 through 9, 9. Nope. What else is there? 0. So there's 10 digits and they can be repeated. And then end with a letter. So again, I know Illinois doesn't have rules. They may have general rules, but then you can go in and get a personalized license plate with all letters with a word. You have to pay extra for that. At least you used to have to, if you got a personalized license plate. But I'm going ahead and typing this on the calculator so that you know what the possibilities are. This is usually the rule, 17576,000. Now, Arizona's got to question themselves, is that enough? Is that enough unique license plates to cover all cars in the state? And if not, they have to loosen up the restrictions, all right? And maybe say you can start with a letter and a digit. So then that means there would be 36 possibilities here, 36, and maybe 36 all the way across, if any letter or any digit could be used in any position. Then that, really adds to the number. All right, but anyway, not repeated. What's the next number? No, I'm not going to type this on the calculator. But if I have 26 possibilities here, how many possibilities do I have in the next position? 25. If I have 10 possibilities of digits here, then how many here and here? 9 and 8. This is the point of replacement or not replacement. And those are common questions in probability. And then 24 for the last, because still cannot be repeated. And then that drops significantly the amount of license plates that you can have. Digits must be even, and the last letter must be a vowel. How many vowels are there normally? What's the normal vowels that are only always vowels? 5. Who else could be a vowel? Sometimes Y. In this case, let's just not make it, but it's a valid question if you ask me. Well, let's just throw it out of there. All right, so digits must be even, and the last letter must be a vowel. And then, I didn't put this in here, but this is repeating. Otherwise, there would be a big problem with this. Then you have to start running scenarios in your head, and I don't want to get into it. This would only be a good question if we could repeat. So digits must be even, and the last letter must be a vowel. So no rule on my first 2 letters. And then how many even numbers are there? How many even numbers are there? 5. 0 is even, if that's what you were pausing on. And then vowels, there are 5 of them as well at the end. Okay? This is why you can't, say, and letters can't be repeated. Because what if you use the vowel in the first 2 sets? Then you have to account for that at the end, and that creates some other scenarios you'd have to write. So. Oh, okay, then I have to go to the next. You have the last page. All right, and then I wish I could have done those questions. I should have thought a little bit more about what's going on here, but that's all right. We can get 9 through 12 tomorrow. All right, and then don't worry about there is no chapter. We're just calling this probability chapter, just like the last chapter was statistics chapter. The book does have some nice stuff in it, but we kind of wanted to organize our thoughts with previous stuff that we've had. So what goes along with this, and actually you can see at the bottom of that page, there's a tree again. And it can be expressed in a little different way. Go to your calculator real quick. And I guess I'll reference this as you go reach into your bag and get your calculator out. So I want you to fish around and find this button, and I'll show it on the video. And then this is going to leak into our notes tomorrow. This is actually the start of what I was going to have for our notes for tomorrow, but I knew we'd have the time and there was a connection, so it is good. Hey, there's that statistics stuff. Yeah. Second quit, clear, get all that junk out of there. And then it is wrong, it's not the stat button. Sorry, it's the math button and then the probability section. And I do have that noted on the notes there. So math and then PRB, those first 3 things are things that we are going to use. I'm sorry, 2, 3, and 4. Not 1, not the first thing. So NPR, NCR, those are permutations and combinations. That's what I'm doing tomorrow. But that exclamation point. So I want you to practice that 6 factorial is what it is, 720. But then I also want you to look at my notes. And I am going to make this no calculator. What I'm going to put at the bottom of this, just so you understand how to deal with a factorial and what a permutation and a combination is tomorrow. Kind of memorize that formula. So, math PRB, write in the notes. And then 6 factorial, this is what it means, and this is what factorials are in general. Whatever factorial you're dealing with, n factorial, you start with that number, and then successfully or succeed by multiplying each number below that number all the way down to 1. Okay, so if that was 8 factorial, it'd be 8 times 7, 6, 5, 4, 3, 2, 1. And that's what a factorial is. So real quick, do 6 factorial, press enter, and hopefully you get 720. And then do 6 times 5, 4, 3, 2, 1, and you get 720. By the way, this is weird, and I want you to lock this in and actually type it on your calculator. So what is 0 factorial? This always blew my mind, and I actually asked one of my favorite teachers of all time, Mr. Samide, I'm mentioning your name on the internet, taught with him at Wheaton North. I remember asking him, why is 0 factorial 1? And that was his answer that I have in quotes. And I'm like, okay, and it's true, because 0 factorial doesn't make sense in the factorial world. All right, but the reason it has to equal 1 is so that our formulas tomorrow for permutations and combinations work. Because if I ask the student 0 factorial, what would your natural response be? What's 0 factorial? Go ahead, say it. 0, because there's nothing there. All right, but it's true. 0 factorial has to equal 1, and that's the only reason that it does equal 1, because otherwise the formula will not work tomorrow. It's very wild, all right? And those things that, for me in math, they just, just blow my mind, but it's just a true statement. So did you type 0 factorial, press enter? That's what I wanted you to do, just to, the calculator doesn't lie, right? So, all right, and then here's your particular tree with the counting principle in there. How many ways can 3 distinguishable objects be arranged? So they just did it in A, B, C. You can pick A first, then B, then C, or A, C, B. Or you can pick B first, or you can pick C first. We know what a chart is, all right? But now what I want you to understand is there's 3 possible ways, then 2, then 1. That's the same as 3 factorial. So the idea of factorials is used in these counting principle scenarios. So introducing you to factorials. Now I'm going to make up some examples so you can do 13 through 16 appropriately without a calculator. All right? I'm going to make up some 3 examples based off of this. So what do I want you to do without a calculator evaluating this? Let's start small. And by the way, the program I used I couldn't find out how to do a fraction button. So I did a division bar like that, all right? And I used parentheses for the more complicated ones. Well, this is what I want you to understand. 5 factorial is 5 times 4 times 3 times 2 times 1. And then 3 factorial is 3 times 2 times 1. Who cancels before I evaluate both top and bottom? The 3, the 2, and the 1. This is grade school mathematics. When I have multiplication on top and bottom, then I can start cross-canceling. It's not like you have to cancel the 1s, but I went ahead and showed that. So what's the final answer? What does this end up being? 20. Well, I'm going to try to do what I did last hour. What did I do? Okay, so let's do last hour's example. Gosh, what did I do? Did I do 12 factorial over 10 factorial times 2 factorial? Anyone, do you have a question, or are you just stretching out? Stretching out. All right, this is one of your formulas tomorrow. All right, this is what happens with a combination. Don't worry about it. Okay, but I'm putting it here so that you know how to evaluate this. Now, 12 factorial, 12, 11, 10, 9, 8, 7, so do you want to write all those out? And the answer is no, you shouldn't have to, and I don't understand why my seniors didn't understand why I stopped at 10 factorial up on the top. Hopefully my sophomores are better. Why did I stop at 10 factorial at the top? Because I have a 10 factorial at the bottom, and each one represents 10. Go, guys. 10 times, 9 times, 8 times, 7, 6, 5, 4, 3, 2, 1. What happens to all those numbers? They cancel. Why would I write them all the way out? I don't understand why the students didn't understand why I stopped there. Okay? So I pull out the 12 and the 11 and then write it as 10 factorial, meaning it keeps going. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then it cancels with the bottom. 10, 8, 9, blah, 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 blah. This is not actually the exact same thing that I did with the other class. I had something a little different, but that's okay. Hey, by the way, 2 times 1, I don't really need the 2, or the 1, I mean. Who does 2 go into? Who does 2 go into? 12. What does 12 become? Now you see why this is a no calculator question. It makes you exercise the factorial idea, cancel when I put it as a division statement, and ends up being a very doable question at the end. Okay, all of your 13 through 16 ends up being under 100 as a final answer. So it's all something that you can calculate. But you want to get nuts? Let's get nuts. Let's say I had 24 factorial over 21 factorial, 3 factorial. And again, you'll find this out tomorrow that this is what a combination formula would end up being. Permutation's a little different and slightly. So same old, 24 factorial is 24 times 23. Oh, I'd be so sad if the students that keep writing this down all the way to 1 and not understanding this basic concept right there. That if I stop after 22 and then write 21 factorial, it just means it keeps going all the way to 1. And now I can cancel that with this 21 factorial. And then what do I do with 3 factorial? I write it out. Now, I will tell you on this what I would do on a test. Okay, so number 1, this is what the student should be able to figure out. Number 2, what's 3 times 2?
6.
Who does 6 go into evenly? 24. So I'm going to cancel these out together. What's 24 become? 4. All right, now, on a test, if it was no calculator, it'd be multiple choice, and this would be one of the listed answers. You get it? So I wouldn't make you multiply it out, but I would make you write it out, cancel who cancels, and then see what you have left over, and I would have a logical thing left over of how a student would cancel. Okay, so that would be a no calculator answer. Because to have you multiply 23 times 22, then 4, that's a waste of time. I'm not checking your grade school mathematics, what Lexi Samuels can do. Okay, so understand that. But on the worksheet, I constructed the questions so they all ended up under 100. So you should be able to calculate the final answer after this canceling. Okay? All right. So, made a mistake on the homework again. Do not do 9 through 12 until we talk tomorrow. And actually, that's what I'm going to start with tomorrow, is those kind of questions. All right. I don't think it's too bad. This does get a little bit more complicated as we move on, though. So it's going to be hard to kind of really disseminate in your mind, what kind of question is this and what's my path? How should I do it? Should I use factorials or should I just put the blanks of the possibilities and how many possible ways something could happen?